In this video, I want to move through a few ideas relating to algebra that introduces the notion of unknown quantities in relation to some other known values. First, let's start with a simple setup using numbered measures to ease our way in. If we have a square with side lengths of 4 units, we can find its area by multiplying the two side lengths together, where 4 squared, or 4 multiplied by 4, totals 16. Imagining this square as a piece of paper and folding it in half like so, we can start to intuitively recognise how 2 side lengths have halved, while 2 others remain the same. And by the nature of folding in half, we've of course halved the area also. So what was once a 4x4 square is now 2 4x2 unit rectangles, each of area 8 units square. Folding in half again brings our area of the smaller square to a quarter of the original, which can be confirmed by recognising our new side lengths of 2x2 gives us an area of 4 units, 1/4 of the original area of 16. Let's now shift to imagining something of the unknown and introducing some variables.
Yo.
Hello, shorty.
We might say, for instance, that instead of the side lengths being a specific number, they could be defined as 2x, that is 2 times some unknown amount. The perimeter of this mysterious square would then be 4 lots of 2x, or 8x in total. And its area, in the same way we found our numbered example, can be calculated by the 2 side lengths multiplied together, so 2x multiplied by 2x. The long form of this equation could be written as 2 times x times 2 times x, where 2 times 2 gives us 4, whilst x times x gives us x squared. And so 4 times x squared gives us 4x squared. Because multiplication is commutative, we could equally have said that 2 times 2x is 4x, and then we can multiply the 4x by x to give us 4x squared. Any way round should result in the final area of 4x squared. Repeating our steps by folding in half as we did before, then 2 half folds, horizontally and vertically, results in our square that is 1/4 of the size of the original, with side lengths half that of the larger square. 2x divided by 2 gives us side lengths of x for this smaller square, so our perimeter will be 4 lots of x, or 4x. And since we have a square, we can once again multiply the side lengths by itself to find the area, where x times x gives us x squared. By unfolding our piece of paper to its original form, we can recognise how we have 4 squares, each of area x squared, so 4x squareds. And this computes with our calculations for the total area, where 2x multiplied by 2x gave us 4x squared. At the scale of a piece of paper, algebra such as this might seem like a pointless exercise in manipulating letters and numbers, especially when lengths can be measured quite quickly. In the real world, its use and value comes in when we have unmeasurable quantities in combination with a selection of measurable elements. So even though we might not have the whole picture, we can build up a mathematical framework to fill in the blanks. We could see applications like this in architecture, where we might be able to measure lengths at ground level, but values rising skyward or extending out into space, as with this Frank Lloyd Wright building, might utilise algebra to calculate overhangs or heights beyond our reach. We would also more readily come across algebra in physics problems, from launching rockets to more down-to-earth modelling of car performance, where times and distances can be brought together to predict speeds, trajectories, or fuel consumption. In another example, I want to think about a square where we know some of its side length, but not the whole amount.
What you doing, son?
Nothing. Just chillin'.
So imagine, for instance, that we have a side length of 3 plus some unknown variable x. Rather than diving into the area first, let's ease our way in by considering the perimeter. As with the other examples we've just seen, the perimeter of any square is just 4 times its side lengths, so 4 lots of 3 plus x would give us 4 times 3 plus 4 times x, adding up to 12 plus 4x. When considering our area, and rather than imagining the total amount straight away, we can approach it by working our way towards the total, dividing our square into 4 quadrants. Let's imagine a line that splits the measure of the side length between the 3 and the unknown variable x. This gives us 4 seemingly different areas. We might start with the known entities first, where the area of this smaller square can be seen to have side lengths of 3 by 3. So its area of 3 squared gives us 9 in total. In the same way, this larger square, which has side lengths of x, can give us our second area of x squared. This leaves 2 rectangles, which although in different orientations, both have one side of length 3 and one side of length x. So their individual areas then would be 3 times x, or 3x. And we could combine these 2 areas by saying it totals to make 2 lots of 3x, so 6x. That means that we could think about the total area of our square, or x plus 3 squared, as being x squared plus 6x plus 9. Visualizing quadratic equations through areas can be an intuitive method to get to grips with the types of algebra that defines curves we might encounter in real life. Parabolic motion, this sort of arcing U or N shape, can be seen more often than you might imagine. Walking a tightrope, a basketball slam dunk, water firing out of a hose, to the launching of a rocket. Each of these curves can be mapped as some form of quadratic equation, containing an x squared, an x, and a constant, which, when added together, combine to form this sweeping curve we call a parabola.
Yo.
What's up?